Hello, I'm Ohio Governor Mike DeWine. I appreciate the opportunity to talk with you today about one of my biggest priorities. That's water. When I created H2 Ohio in 2019, we set important goals to improve Ohio's water and specifically to reduce algae bloom on Lake Erie. It's a long-term effort. H2 Ohio is creating wetlands and working with farmers to adopt conservation practices, and we're making big strides in the right direction to improve Ohio's waterways. This work would not be possible without the commitment from Ohio's farmers. I appreciate our farmers who immediately answered the call to adopt practices that we know will reduce phosphorus runoff from farm fields and improve Ohio's waterways. More than 1.5 million acres of Ohio's farmland in the western Lake Erie Basin are currently enrolled in H2 Ohio. And my proposed executive budget would make this program available to farmers statewide. As part of H2 Ohio, farmers are planting cover crops, using new and cutting-edge technology, and following nutrient management plans to make sure they are doing everything they can to prevent nutrients from leaving their land. The use of technology and conservation practices are critical in pressing forward with our water quality goals. In this webinar, you will hear about the work being done through the Conservation Technology Information Center, the Nature Conservancy, and Heidelberg University that is bringing to light important data on conservation practices that reduce phosphorus runoff into Lake Erie. The collaboration between academic researchers, conservation groups, farmers, and state partners is important for addressing Ohio's need for improved water quality. I want to recognize many of you who uphold the strong partnership between the agricultural and environmental communities. These partnerships are the backbone that connect farmers to conservation. OACI, the Ohio Agricultural Conservation Initiative, brings together these communities to stand as united advocates for clean water. OACI's work has been instrumental in H2 Ohio's success. So to all of you, thank you so much. Through your everyday work, you're not only protecting Ohio's water, but more importantly, you're improving the lives of all Ohioans.
Hello, everybody. Thanks for joining us today. My name is Soren Runquist, and I'm a data scientist with Regrow. Regrow in general is a company that's using satellite sensors and other data to track, monitor, and model regenerative ag practices and quantify their impacts on carbon solutions and other things like water quality. So in respect to water quality, Regrow is monitoring the landscape to better understand how we at a field level can intervene to identify opportunities to improve water quality through best management practices on agricultural landscapes. A few of these avenues would include using these data for targeting, identifying areas that would be of a higher priority for co-benefits for water quality, biodiversity, water retention, and carbon sequestration. Using these data to track the effectiveness of conservation. Where are areas where we can see these practices being adopted on the landscape and also persisting on the landscape. They can also be used to understand where we're at and where we want to go, establishing baselines, trends, figuring out those regional dynamics to help us allocate resources to better improve the effectiveness of these field level practices. And finally, as you'll learn later on in this presentation, how these field level data can be used in model inputs to really quantify the impacts of agricultural landscapes. So at Regrow, we are generating field level scale data on regenerative ag practices, and those are being made primarily on three platforms. We offer a solution called Sustainability Insights, which provides access to Regrow data for planning and prioritizing sustainability outcomes. We have a solution called MRV, standing for Measuring, Reporting, and Verifying, which allows users to customize their program needs, like individual fields, to verify the impact of regenerative ag. And finally, we offer a solution called Monitor API, which gives users essentially bulk access to Regrow data, allowing for development of an individual tailored solution for that customer. So I've talked about kind of how you can get these data. What are the actual data that we're providing? Some of our key products that were developed through partnerships with TNC and CTIC are the OpTIS products. OpTIS is an acronym for Operational Tillage Information System. And it was essentially started out as a way to classify tillage on the landscape in row cropped areas. So we still offer residue and tillage classification. We've evolved the algorithm to be more dynamic to track the individual date in which a field was harvested, and thus track the persistence of residue to the next transitional event on that season. And we're also scaling our products to be more global. So we're incorporating more standardizing, I should say, more inputs in terms of modeling for things like precipitation. One evolution in the OpTIS product was the development of cover crop detection with using satellite sensor data. We can track fields for the absence or presence of cover crops after a harvest event. And I should note that these cover crop detection are instances in which the cover crop was planted to essentially protect the soil and not be harvested as a commodity. We have updated that algorithm as well to be more temporal in terms of the quality of vegetation. So having more context to the quality of cover crop. Was it, killed over the winter time? Was it very rigorous and healthy green? Providing that range for quality, as well as we've made the algorithm dynamic to account for the difference in growing conditions based on regions. So cover crop will behave differently in North Dakota than it would, let's say, in southern Mississippi, and thus our algorithm is sensitive enough to track what the definition of healthy vegetation would mean in those respective areas. And then we're also being very careful to track areas that are not confused with perennial grass. So we want to make sure we're tracking cover crops on areas that were previously planted to row crops. Outside of that, our products are evolving to provide solutions for grazing and the potential to sequester carbon on grazing lands. We also identify crop type, and we have the power to monitor the health of vegetation temporally. Those products are then kind of turned into key performance indicators or tools, essentially, which would include the soil organic carbon potential within a field or a landscape, the ability to monitor and evaluate program adoption, site selection targeting, and again, establishing a baseline or a trend for an individual program, field, or region. So today I'm going to focus on two of the Regrow products, cover crops and conservation tillage, and we're going to just run through some historical data and talk about kind of trends and interesting key points of those data. So here, what we're looking at is temporal profile of cover crops from 2015 to 2021. And as you can see, the profile is going upward. The upward trajectory indicates a solid growth curve of around 66% from 2015 to 2021, with about 15 million acres of cover crops planted on row cropped areas in the continental United States. So it's good to know we're planting more cover crops since 2015, but where are those cover crops being planted? As you can see by this map, showing the acres of planted cover crop in 2021, over half of those acres in 2021 come from the areas that need it the most, kind of the Corn Belt, where it's as a high density of row cropped area in those states. You can see a handful of states, 9 states, account for more than half of all that cover cropped area. This next slide shows cover crop planted and then the rate of cover crops for an individual state's row cropped area. So these are kind of more or less an adoption rate, for lack of a better term. But those percentages you can see in the deeper greens would indicate higher row cropped areas protected with cover crops. And again, in 2021, a handful of states had 5% or greater area protected with cover crops, which was much higher than the national average of about 4.4. And you can see there's a little more adoption in kind of the eastern seaboard and the southeast. However, they have much smaller row crop universes in comparison to the upper Midwest and Corn Belt regions. So pivoting away from cover crops and looking at temporal profiles of conservation tillage, we can see from 2015 to 21, there's been a slight drop of about 12 million acres. However, the y-axis is somewhat detailed, it looks a lot more dramatic than it is, but that 12 million acre drop equates to a pretty flat trend line. So in total there in 2021, there was about 106 million acres of row cropped areas classified as conservation tillage. So again, if we look where are producers adopting conservation tillage, we can see that 7 states account for kind of almost half of the entire conservation tillage universe. And a lot of those states tend to be kind of in the upper Great Plains, in kind of wheat country, as well as kind of Iowa and Illinois and Kansas. So again, if we look kind of similar to what we did with cover crops at the percent of the row crop universe where conservation tillage was adopted, we can see in 2021, the upper Great Plains had a quite substantial area, more almost 6% points higher than the national average, and South Dakota, Indiana, Ohio, Montana, Kansas, and North Dakota. So with these field level results, we can look 30,000 foot overview of the entire continental United States, or we can start digging deeper. And what this slide is showing is cover crop adoption on the left and conservation tillage adoption on the right for the state of Ohio. And Ohio gets a gold star because they're doing above national numbers in terms of averages, with around 400,000 acres of cover crop adoption in 2021 and 3.6 million acres of conservation tillage adoption in 2021. So outside of the state, again, with field level data, we can get more detailed in kind of how this adoption looks on a spatial basis. We have the ability to aggregate these data at political boundaries to explore kind of associations with policy. So you can surmise some relationship between federal cost share at the county level compared to what's being mapped on the landscape. And these two maps are county maps of cover crop adoption on the left and conservation tillage adoption on the right, within political boundaries. Also, we can turn these field level data into aggregates on environmental boundaries, things like watersheds. These are small scale watersheds known as HUC 12s. And the data again is then aggregated to take these and input them into models, let's say, to understand kind of impacts of nutrient loading on agricultural landscapes. And from there, it's a good segue to hand it off to my good friend Dave Gustafson to tell us about what he's been doing with watershed level data. Thanks.
Well, thanks, Soren, and it's always a pleasure collaborating with a fellow Scandinavian. So I will be speaking about some regression modeling, and you're going to hear about different forms of water quality modeling later from our colleagues over at the American Farmland Trust and the Ohio State University. But I'll be speaking specifically about some regression modeling work that we did here at CTIC. This work was part of an overall project called PlusUp, which I'll briefly describe. And the regression model work was used OpTIS data as input. And I'll briefly describe all that and some of the key findings and implications here. But as you can see on the right side of the slide here, this particular part of Ohio, that is the Western Lake Erie Basin, has been the focus of a lot of work. And I know Governor DeWine mentioned this in his introductory comments, that it has been for quite a long period of time, a focus for the H2 Ohio effort. But our program was actually funded by EPA, the Great Lakes Research Initiative, GLRI, and we called it PlusUp, the Phosphorus Load Reduction Stimulation Program. Our key partners on this particular project were Heidelberg University, who provided water monitoring data, as well as some modeling that I'll briefly describe. And then another key partner was Bayer Crop Science, who came in and purchased the phosphorus credits that we were offering to farmers in this basin. This whole program was a market-based approach in which we paid farmers for reductions in dissolved reactive phosphorus, which has been linked directly to the size of the harmful algal blooms in Lake Erie each summer. And we paid farmers $100 a pound for their avoided dissolved reactive phosphorus loads, according to their adoption of either no-till and or cover crops. And the PlusUp payments were made regardless of their participation in other programs, including the H2 Ohio. The modeling work that I performed was affiliated with using, again, OpTIS data as input, or X variables in the regression. And then for the Y variables, I was using the water quality monitoring data coming directly from Heidelberg University. So the watersheds that were included are shown here. There were 8 different watersheds that range from very small size, almost invisible on this map. Actually, Lost Creek is only 11 square kilometers. But some of you on this call are probably aware of the fact that Heidelberg University has been monitoring water quality in watersheds such as these, going all the way back, actually, I believe, to even the late 1970s by Dr. Dave Baker, who's no longer with us, but he founded this whole program, and Laura Johnson is now the director of the effort there of Heidelberg, and was a very close collaborator on this project, and provided the water monitoring data as well as the watershed size data that you see here. So we're going from rather large watershed, the Maumee River Basin, some 16,000 square kilometers, all the way down to the very small Lost Creek. And what the folks at Regrow were able to do is, because we provided these shape files over to them, they were able to then turn around and provide us the cover crop and conservation tillage adoption data for each of these individual watersheds as input to the regression modeling. So one of the things that the folks at Heidelberg do is their monitoring stations are associated with USGS gauges, so we can do very precise calculations around discharge. And it's actually the spring and summer discharge that is most closely correlated to the size of the harmful algal bloom. And you could see here for this time period of interest that we were looking at, that 2011 was a very high runoff year, otherwise, because of very intense precipitation. But numbers bounced around. I don't think there's a meaningful statistical trend there, but the overall trend over time, because of climate and other issues, is probably for heavier spring-summer discharge in this particular geography. The monitoring data for these watersheds is shown here. Again, this came from Heidelberg. And not surprisingly, on the left, if you just look at how much phosphorus loads took place, it's very tightly correlated to the much heavier discharge that took place during, for instance, 2011. But when you divide this through, in other words, you take the load of dissolved reactive phosphorus that's coming off of each of these watersheds and divide through by the discharge, it basically evens out. And as I'll show in a moment here, it's because DRP is essentially linear correlated with discharge, which should be no surprise to others who have investigated similar data. So those are essentially the Y variables in the regression that I just showed you. And then looking at the X variables, this is the OpTIS data on conservation practice adoption in these very same watersheds for the very same years. And the numbers bounced around a little bit. For this particular geography, the year 2020 was the year where the prevent plant issue had the cover crop numbers go up. And I should also indicate that what I'm actually showing here is total winter cover. So this includes both cover crops and winter wheat, which and those are distinguished, as Soren briefly mentioned in their data set. And then on the right, we see the adoption of conservation tillage, which again bounces around a little bit for these watersheds, but overall net was fairly flat during this particular time period, and corresponded to, in around overall average of 50% of the row crop area in this region is in a conservation tillage defined as greater than 30% crop residue. So then the name of the game was to simply feed all these data to a suitable statistical regression modeling tool. The one that I used was JUMP, which comes from SAS. I'm sure others who are out there who've done any statistics work are probably familiar with this particular tool. It's pretty handy and was used to create the charts that are shown here. So on the left, we can see, as I've already mentioned, actually that DRP, that is dissolved reactive phosphorus, is very tightly correlated with discharge. No big surprise there. And then when you attempt to regress DRP directly across both winter cover and conservation tillage, it's relatively flat, particularly conservation tillage. In other words, there doesn't seem to be a clear correlation between the level of adoption of conservation tillage and the reduction of DRP. Maybe a slight correlation directly with DRP for winter cover, but for sure not statistically significant. But as a next step in the regression process, what I simply did was to regress, instead of DRP itself, I divided through DRP by the discharge. So now we have DRP per centimeter of discharge. And now we start to get a slightly stronger correlation with winter cover. It's not overly convincing and just borderline statistically significant, but it's certainly in the expected direction and much stronger actually than the only slightly negative correlation with the level of adoption of conservation tillage. But again, even for conservation tillage, the correlation is in the expected direction. That is, if you have greater levels of conservation tillage, your DRP per unit of discharge is indeed reduced. So then what I did was to take those regression models that were developed and then do some very simple scenario development. Here, this first scenario is where I take winter cover from its current level of 10% adoption up to 20%, in other words, a 10% increase, and show that the reduction in DRP, if we had that happen across the entire study area, would be a 15% reduction, which I think is significant. However, for conservation tillage, if we go from the current level of 50% and we somehow got 10% of the overall watershed to switch over to conservation tillage, the regression is telling us that the reduction would be quite small, only a couple percent actually. So with what we were able to learn by using the OpTIS data as input to this particular study is that indeed DRP was confirmed to be linearly correlated with discharge. No big surprise there. So we then performed all the regressions using DRP per unit of discharge, and we found, as I've already mentioned, that winter cover was more significant than conservation tillage. P-value just a little bit above 0.05, but I think is perhaps not statistically significant, but of importance for sure. And then we did, with this scenario analysis, we found that investing in cover crop adoption would actually looks like it's the more greater payback from an overall policy perspective, and that if we were to get another 10% adoption of cover crop, we would be far more effective, 6.5 times more effective than getting a 10% increase in conservation tillage adoption. So as I say, that has, we believe, very important policy and incentive implications. We have now reported all of these findings to EPA GLRI, who again was the funder of this overall project, which ended at the end of calendar year 2022. And we do have, we're thinking about what we can publish here, and I've begun reaching out to the various collaborators, including Laura Johnson and others at Heidelberg, and then our collaborators at Regrow as well, Soren et al., who you just heard from, as to whether or not we should go ahead and write this up for publication in the peer-reviewed literature. So anyhow, thanks for your attention here. And now you will be hearing about additional applications of OpTIS data for water quality modeling from our colleagues over at the American Farmland Trust and Ohio State University. So thanks very much.
Thank you, Dave. Good afternoon, everyone. I'm Mark Wilson with American Farmland Trust, and I'm fortunate to be joined in this presentation by Dr. Asmita Murumkor from Ohio State University. I say I'm fortunate because Asmita is an experienced water quality modeler, and I am not. I'm an agronomist. We make a good team. During this presentation, Asmita will highlight the watershed models that we are using and how OpTIS data will add to the value of our modeling results. But before we hear from Asmita, I'd like to provide some additional context to our presentation, and that is I'd like to talk about the overall project under which the modeling is taking place. The goal of this project is to reduce nitrogen and phosphorus loss from farmland in the upper Scioto River watershed, and thereby protect local drinking water and minimize hypoxia in the Gulf of Mexico. The objective of this project is to change the paradigm of how conservation is funded. In particular, we would like to pay farmers for reasonably assured environmental outcomes rather than paying them for a practice that's randomly implemented on the landscape. The methodology that we're using in the Farming for Cleaner Water project is we're relying upon high-resolution remote sensing data, i.e. OpTIS, field-scale watershed modeling, precision conservation practice siting, and water quality monitoring to assess field sensitivity for nutrient loss and what level of agronomic and conservation management is needed to mitigate that loss. The current investment in our project stands at $1.75 million, and our principal funders have included the Hart Charitable Foundation, US EPA, and the United States Department of Agriculture. We're working closely with the National Center for Water Quality Research at Heidelberg, as well, of course, as the folks at Regrow and the Ohio State University. The webpage for this particular project has a unique story map, which I'd encourage you to visit. Now I'd like to introduce you to the Upper Scioto River watershed. The study area contains 30 Huck 12s. It's approximately 687,000 acres with more than 27,000 individual fields. 80% of this watershed is agriculture, and of that, 70% is row crops with 65% corn and soybeans. Why the Upper Scioto River watershed? Well, it provides drinking water to more than 1 million people in Columbus and surrounding communities. The issue that we are seeing in this watershed is there are seasonal nitrate spikes, And Ohio EPA has identified this watershed as having the second highest nitrogen and phosphorus load after the Western Lake Erie Basin that Dave discussed. So with that, I'd like to turn it over to Asmita, who will present the modeling.
Thanks, Mark, for a great introduction about our project and the watershed issue in the Upper Scioto River. Hello, everyone. I'm Asmita Murumkar, research scientist at the Ohio State University. Today, I'm going to talk about the watershed model soil and water assessment tool we are developing for the Upper Scioto River watershed, which can predict the water quantity, quality, sediment, and soil carbon, as well as greenhouse gas emission at hook level, field level, as well as watershed level. So this is the schematic representation of data inputs required to develop a SWOT model, stream topography, which can just delineate to so watershed, and soil land use topography, again, delineate to the hydrologic response unit, which is the smallest unit of the model. Once we have a SWOT model, we can run the different test scenarios, such as conservation practices, to see the water quality benefits of these practices at field scale as well as watershed level, as well as we can targeting and prioritizing at hook level practice implementation using the SWOT model. Here, high resolution SWOT model means we are developing for Upper Scioto as delineating the HRU, hydrologic response unit, to the farm field scale, so that we can see the impact of these conservation practices at field level and overall at the watershed level. Once we are putting all this input in the model along with the climate data, we are going to run the calibrate the model at the watershed outlet as well as sub-basin level, and validate using the edge of field data for the practice validation for the water quality as well as hydrology. So what kind of data we really need to build the high resolution model? First is remote sensing data. We are relying on OpTIS data, such as crop rotation, cover crop, and tillage practices, because we need this information at the farm field level. Then the soil test phosphorus is really important as related to legacy phosphorus and non-legacy phosphorus fields. We are using the county level STP distribution to get the heterogeneous representation of soil P values at our HRU level. Based on this crop rotation, cover crop tillage practices, along with this STP distribution, we are going to use the manure and inorganic fertilizer application at this field level based on the location of permitted and unpermitted facilities. I'm going to use one of the graduate students develop one protocol how we can allocate these manure applications at the field level, and as well as like based on the STP values and crop needs. Along with this, we are going to link these other practices, such as the application of this fertilizer, such as subsurface application, tile drainage, spacing information based on the Ohio drainage guide, and wet end location. So these are the input data required for the SWOT model. So first, it's really important for us to get the high resolution field level information related to type of crops, crop rotation, cover crops, and tillage practices. As you see in the field, we have the HRU delineated to the farm field level, and we are relying on OpTIS data. So this is the HUC level information we received for 3 years, 2018, 2019, 2020. In first year, you can see the percentage of corn in that particular HUC. And in second row, you can see the percentage of soybean in that HUC in 2018, 19, 20. You can see in 2019, we have a wet years. There is not a great plantation done in 2019 based on, we can see the distribution here of corn soybean information. With this, like a cover crop type of crop and crop rotation, it's really important to have the information about cover crops such as winter wheat, along with the other cover crops, rye, alfalfa, to put as an input in our model. along with the tillage practices. Here I'm showing you the two different crops. First one is the cover crops with no till. Second one is like a no cover crop with conservational till. So you can see in 2020, there is little bit increase in the cover crop with the no till, but you can see the percentage with respect to first, like cover crop with no till is not that high compared to the no cover crop and conventional till. Once we have sort model calibrated with the sub-basin as well as the watershed level, which kind of practices we can really simulate through sort model. Here is the example of this: conservation tillage, winter cover crop, grass waterways, nutrient management. We can run the different scenarios along with we can bundle these scenarios together to see the impact of the stacking of practices on hydrology as well as water quality. So this is really great. You already listened the video from Governor Mike Tuan about the H2 Ohio program, and we're gonna evaluate this H2 Ohio program for the water quality benefits in the upper Scioto River watershed. So these are the top 10 practices related to nutrient management, erosion management, and water management. We are going to run the 3 different scenarios. First one is going to see the practice sensitivity. That means like see which practice has the greatest potential for water quality outcome. So we're going to run the sort model practice at a one time and get the highest benefit, how much like really benefit if we have 100% adoption of cover crop in the region. So we can really rank these practices. In the second scenario, we are going to run by bundling all these 10 practices together based on the first enrollment of our H2I program in the region to see the till now effect of this adoption of practices on hydrology and water quality. And then second one is based on these 2 run scenarios. Third run we are going to do to see the future implementation plan, to see the success of the H2 Ohio program in the region. So it will help to guide the future implementation planning in the region. Along with once we have the field scale sort model, we can really integrate with the other model to get the integrated model which helps to resolve some issues, just relying on one model, but we can integrate sort model with other models such as ACPF, agriculture conservation practice, as agriculture conservation planning framework developed by USDA ARS group in Iowa, which is a geospatial tool helpful to tell us the suitability of that particular field for a particular practice based on the soil, slope, and land use. So we can really target the field, which practice is suitable for that, put that implementation and see the effect of these at field level as well as watershed level by using the sort model. Another one is, again, NRCS developed tools, stewardship tool for environmental performance, which evaluates the ecosystem metrics such as water quality, soil carbon, greenhouse gas emission in response to farm scale management and practice adoption and actions. So we are using the OpTIS field segment boundary here right now to run this step tool, which is the qualitative assessment useful for the payment for performance. So here is our first run. The Houston engineering consultant ran this tool at field segment data to see the sensitivity score of nitrogen soil leaching potential based on the soil type and topography. You can see the red colors is showing the high potential of nitrogen soil leaching. So we can really use these fields for targeting the practice implementation. Here we are going to use the OpTIS field level information such as cover crop and tillage practices to see if we can able to change this color to green and then like improve in terms of water quality runoff from that field. These are our contact information with Mark. Thank you for this opportunity.
Great. Thank you, Asmita and Mark. This has been just fascinating, and I applaud you and the rest of the panelists for your precision on time, not just sharing great information, but doing it in a really timely way that allows us to have a little bit of a question answer period. So I'm Steve Werblow, representing CTIC, and I'm just going to moderate the question and answer period. There is a Q&A chat box. You can access that down at the bottom of your screen and type in questions. We've got some great questions already that we'll start with, and I encourage folks to add more to that list. I'm going to answer one that was answered by text, and that was a question about the availability of recordings. So this recording will be posted at ctic.org /OpTIS, and I'm putting that in the chat right now. We'll try to get that to everyone. That website also, or that web page also includes previous webinar recordings as well. So there's more angles and details on OpTIS there. So now with that, we're going to get to the first question, which is from Steve Davis. And we're going to point this one to Asmita. And the question is, what limitations of this analysis are due to differences in maybe in the subwatersheds? For instance, subwatershed A has high livestock concentration and more legacy phosphorus than watershed B, which doesn't, or other soil or cultural differences. So Asmita, I'm going to hand that to you.
Thanks, Steve. It's a great question. With the, like Jeffrey Cass, he was working in Maumee River Basin and developed that, how we can really apply manual allocation in the model based on the permitted and unpermitted CAFOs. And we do have another project in Maumee focusing on legacy P versus non-legacy fill, how much we can really target to these fills. So right now, this is our first phase from the Ohio State. We are developing this model, but I feel like having the field level information related to soil test is really important in the model too. But based on our recent Libby Dayton's 2020 paper, county level information is going to be helpful to have the heterogeneous distribution in our model, which will compare to what we have published in other two first phase of models, where we use the one single STP values or the region. But now with the help of these information, we can improve this in our model, as well as having this CAFO locations is going to be helpful. But one thing here I want to mention that when we are having this model, as we're not running in dynamic way related to STP values or like a manure data into the model. Recently, we are going to use 2017 as a CAFO information in our model.
Steve, this is Dave. I was just trying to follow up on Steve Davis's question. I believe you were asking me the question, Steve. So yes, there are absolutely a whole bunch of other factors that are involved in the overall correlation. And as you, I'm sure, already noticed, there's tremendous scatter in the kind of regression analysis that was very simple. I was just plugging in those two parameters, and I am certain that things such as you've identified, especially around livestock prevalence, are undoubtedly associated with some of the variation that we haven't explained. We haven't explained more than, I would say, 10 or 20% of the overall variation in the DRP at this point. So there's a huge opportunity to collect information like that. I was basing my analysis using only the OpTIS data and just focusing on the relative importance of cover crops versus conservation tillage. So I think there for sure are many other variables that one could seek out to try to plug into that analysis. And in fact, I would point to the work that Asmita is doing down in the Upper Scioto as a perfect example of chasing down, for instance, manure applications, fertilizer application rates, all sorts of things that would have improved the overall performance of the regression analysis. So thanks for the question.
Thanks, Dave. And thank you, Asmita. I'm going to reach back to a question that Sid Chaudhry had posted just to make sure that people hear the answer. So Soren, I'm going to ask you just to describe how you differentiate between cover crops and say double crops or cash crops, winter cash crops, and how you validated the survey because, or how you validated the model with field work, because I don't want to lose that to just the chat box.
Sure, Steve. Great question. In regards to differentiating cover crops with cash crops or crops that were planted in the winter that were intended to be sold as grain, typically we actually, the entire landscape will actually do crop identification. So we'll know kind of if it's indicative of a situation where a crop is more likely to be a commodity. So what that means is the timing of a double crop in a winter crop scenario, or winter crop in a double crop scenario, it would be that the crop would emerge and grow and then senesce and be harvested typically later in the spring season or into the summer. And thus a cover crop is going to be terminated right in the spring and typically given the producer enough time to actually prep the field to plant the following crop. So crop identification is essential in kind of debiting those winter commodities from crops intended just to be cover crops. And then in terms of validating these models, we use a plethora of data sources. Internally, we actually drive windshield surveys in which we're going into these row crop landscapes in a car and documenting as many ground control points as we can get for percent green cover, percent residue cover, previous crop, standing crop, cover crop, no-till, etc. And then using those to kind of assess the quality of our outputs. We're also using data procured from state agencies, NGOs that are kind of either handing out funds to help producers adopt cover crops or working with big companies to kind of optimize their supply sheds to adopt cover crops. And using those data at varying levels of spatial granularity. So in some cases, it might not be an actual field. It could be kind of a watershed or a county, as well as along those lines, federal cost share data, which is typically at the county resolution. So I say all that because all these data have kind of varying levels of quality and resolution. But in total, we can holistically use each individual ground control piece to kind of validate and give us some general accuracy as to how our products perform in specific regions.
Great, thank you. And I'm going to keep you on the stand for one more second because you mentioned spatial granularity, and Aaron Hurd has a question about temporal granularity or timelines. What's the lag time due to collection and analysis of the data related to land use and cover crop use? So is that an annual release or 6 months or monthly? What's your timeline?
Yeah, that's a great question. And that varies by product, but specifically for cover crops, it typically was an annual update. But as Regrow is growing and kind of making our process more efficient and plugging into more kind of real-time sources for these data, we're optimizing that cadence to be more or less maybe 6 months, ideally 3 months. But yeah, it's kind of in our right in front of us to kind of get a quicker response in terms of inputting the data, classifying the data, and getting it back to the customer. But yeah, typically it's been an annual report, but I think we're getting closer to half a year for kind of a response time for cover crop products.
That's tremendous. It's a mammoth effort. I'm going to go to a question from Zoe Thorsland. It says, for the USRW project, are nutrient use efficiency products that improve water quality by reducing nitrates and improving phosphorus uptake considered as a practice to drive desired environmental outcomes?
Are you addressing that to me, Steve?
Yeah, let's. I think you're probably the best source for that one.
Well, certainly those products are very effective at reducing, for example, nitrogen, which is the nutrient of interest or focus here in the Upper Scioto River watershed. We do have ability to look at a variety of different additives to products like inorganic fertilizer, but specifically one of the components of our project is looking at using a fertilizer, a phosphorus fertilizer known as triple superphosphate. This phosphorus product does not include any type of a nitrogen molecule. So instead of using monoammonium phosphate, we are trying to incentivize the use of triple superphosphate, which will not release a nitrogen molecule in the fall, which is typically a fallow period. And that nitrogen molecule is often lost to the environment under such circumstances. So we're excited about the opportunity to look at these additional additives and as well as unique fertilizer products.
Outstanding, thank you. And while we're on the Scioto River, Upper Scioto River watershed question, this one is for Asmita. Will the Scioto model differ much from the Maumee model that you also cited?
Yeah, this will differ with our second phase of Maumee model because we are focusing here SWOT plus, which is a completely restructured version of model where we can really bring the high resolution information, and as well as there are new developed tools related to structural practices. So this is going to be differ with Maumee as we are focusing on SWOT plus development for the Upper Scioto.
Excellent. So now there's a question here, and I can put this to Mark as an agronomist, or Asmita as the modeler, or both. Question here on the role of soil stratification and whether that has any impact on the movement of nutrient in the system.
Well, we do see a significant stratification of phosphorus in particular within a soil profile when it's in a reduced tillage or no-till situation. So that is something that we need to consider and look at. With stratification, it's not so much of a factor with nitrogen movement. Nitrogen being very capricious tends to leach and move down through the profile. So it's pretty uniformly passing through that soil profile. Leave it at that.
Great, thank you. We have time for one last question, and I'm going to ask Ashley Hammock's question. And she's pointing to the second and third presentation. So that's Dave and Mark and Asmita. Linking concepts, it seems like a reoccurring issue that there are hot zones or animal producers who also grow crops that may be diminishing the effectiveness of broad scale conservation practices for a watershed. Have you investigated that aspect of that phenomenon, I guess?
Well, I'll hand it over to Asmita, but except to say that I turning to Soren for a moment. I don't know if you folks have thought about that from a overall your new monitoring products that are looking at animals and grazing lands, et cetera. But I think there's an opportunity there. I agree that this is a super important factor, especially with phosphorus, but I'm sure with with nitrogen as well. So I think there's an opportunity to improve both the modeling, but also the data sets that are available to plug into the models.
I'll chime in quickly. Yeah, Dave, Regrow is actively looking into kind of building solutions that, sourcing feed as well as location and size and type of animal relative to where that feed is being sourced to kind of equate some impact from animals. Thanks.
That's beautiful.
Yeah, and same in SWOT model. We are taking this K4 location, the animal counts into the account, how much they produce in terms of like phosphorus, and then we are using near fed location of that to apply the manure first. So that's the strategy we are taking into account within the 5 to 10 miles of that radius of that location.
Excellent. Thank you. Okay, we're going to squeeze one more question in here. Ben Gleason asks, and this is for Soren, how does OpTIS compare to ground truthing or other methods?
Typically in the United States, for cover crops, we're seeing a range of kind of 70 to 80% accuracy, which we find promising. With all things remote sensing, you typically have periods where weather is very impactful on kind of your classification times, winter, clouds, etc., snow covering fields. So yeah, that accuracy is somewhat general because again, we have in some regions we have really verbose, great data. In some regions we don't have as much data. So we look at that as kind of an opportunity for this kind of industry as a whole, is kind of getting standard ground control at the field scale would kind of be a benefit to a variety of remotely sensed products as well as models, kind of help calibrate that variance on contrasting regions, on contrasting definitions of cover crop in general, regardless of just kind of a yes or no cover crop, but how good was the cover crop? Did it emerge? Was it winter killed, etc. But yeah, typically, 70 to 80% range is where we're landing with our cover crop products.
That's great, and hopefully we'll be able to continue to build on that, as you said, as members of the audience and members of the panel continue to use those data and put it to work. I'm going to we're going to wrap this up. I'm putting in the chat a story map that talks about the Upper Scioto River Watershed Project. Also encourage folks to stop by ctic.org/OpTIS. We've got the visualization tool up there. The data are available at the county and crop reporting district level, and you can actually go play around with the sliders and take this out for a test drive. So we encourage you to visit. And I want to thank everybody for being here today and sharing all this great information. Thanks so much.
Yeah, and I want to turn to the co-panelists on behalf of CTIC. I know Ryan couldn't be here, but just a huge thank you to you, Soren and Mark and Asmita. It was awesome to have you join the panel today. So stay tuned. There will be more webinars coming up soon. See everybody.